Welcome. In this video, we're going to be looking at more exponential models. Now, we're not going to take the time to fill out this diagram in the top of your notes, so we can skip that. We're also not going to do these two examples. These are similar to lesson 6.1, the second part of 6.1. So if you want to, if you don't know how to do these types of problems, you'd want to make sure that you watch that video. What we're going to get to is another model, another formula we could use that represents exponential growth or decay. And that's this compound interest formula. So this is very similar to the formulas that we saw in the previous video where we had 1 plus r to an exponent. Well, this is using an idea of compound interest. Now, compound interest can be compounded in a number of different ways. What that means is that instead of the interest being given to us all at once at the end of the year, we're going to take that interest and we're breaking it up into smaller pieces. And so if it's compounded quarterly, that does not mean that we're getting the same percentage rate 4 times a year. It means we're taking that percentage rate and dividing it up 4 times a year. So you think about there's 4 quarters in $1. So if it's compounded quarterly, n would be 4. If it's a situation where it's compounded monthly, n would be 12 because there's 12 months in a year. If it's a scenario where it's compounded weekly, that means that there's 52 weeks in a year. So that means that the percentage rate is broken up into 52 really small pieces and added into your account over the course of a year. And annually just means that it's incorporated at the end of the year. Semi-annually means twice a year. So that's what n means in this formula. Now the rest of the pieces in this formula, P represents your principal amount. That would be like your original investment. Or if it's a house that you're purchasing, it's the original purchase amount, or a student loan. It could be any of those. So a principal could just be it's a original amount. The original dollar amount is your principal. So it could be investment, it could be a purchase, or it could even represent debt. The R represents your percentage rate, but we need to change that to a decimal. Okay, we don't add it to 1, we don't subtract it to 1 because that's going to be done here. So we don't do that twice. So, but we do change it from a percent to a decimal. That is very important. N represents the number of compoundings in a year. Which we already talked about in that box below. And T represents your time in years. So if it's ever in terms of months, like let's say if it says 18 months, we don't want to use 18 for our value for T because that would be referencing 18 years. So where 18 months would be 18 divided by 12 would be 1.5. So it'd be 1.5 years. So we'd do 1.5 if that were the case. All right, so let's just jump right into reading a story problem so we can see how we would use this. It says Tamira invests $5,000 in an account that pays 4% annual interest. How much will there be in the account after 3 years if the interest is compounded annually, semi-annually, quarterly, or monthly? All right, we're going to do a couple of these together, and then I'll just tell you what the other ones would be, so that way you could just see the pattern. So let's start with what it would be if it was compounded annually, so where n is 1. So if n was 1, we're going to use that formula. Scroll down so you can see it. So the principal amount would be the $5,000. Our rate, the 4%, we have to change that to a decimal. So 0.04 is what we're going to use. Compounded annually, n would be 1. So our exponent's going to be n times t. So it would be 3 years. And our number of times it'd be compounded in those 3 years would be once every year. So 3 times 1. And I'll just tell you that when you do this on your calculator, we'll round to the nearest penny since we're dealing with dollars. So we get $5,624.32. All right, well, let's see how much this is going to change if we do it semi-annually. So semi-annually is going to be using the same information except for instead of n being 1, n is going to be 2 this time. So our exponent out here, we'd have 3 times 2. Now this time when you type this in your calculator, you get $5,630.81. So about a $6 difference if it's compounded twice a year. So it's using the same percentage rate, but it's compounded twice a year instead of just at the end of the year. So yeah, not significant right now, but over the course of time, as that $5,000 increases in value, it's going to make a bigger difference. All right, let's do another one of these. So I'll show you again how to just set this up. So let's do when it's quarterly. So if it's quarterly, n would equal 4. So again, everything else would be the same, except for n would be 4. So we would have then also 3 times 4 as your exponent. And this time you get $5,634.13. All right, so now we see that the increase. So now it's $10 compared to what we had compounded annually. And let's do one more. So this one we'll do for if it were compounded monthly. So this represents every month a little bit of percentage rate gets put back into our bank. So over the course of the year, we're gaining interest on our previous interest during the course of the year. Exponent would be 3 times n or 3 times 12 because that represents 36 times that we've broken up. And this time when you get your answer, you get $5,636.36. So about a $12 difference compared to compounding annually versus compounding monthly. All right, let's look at this next one. So I want you guys to try setting this one up on your own using the fact that this time the mortgage is $280,000. It compounds monthly. So we're only going to do it once this time at a 3.25% annual rate. So we have to change that 3.25% to a decimal. How much will I pay after 30 years? And so you would put your time would be 30. So I want you guys to set this one up and see what you get as your answer. Right. So here, when you plug that information in, again, 3.25% as a decimal should be 0.0325. We don't add it to 1 because, again, that's already happening in your formula there in your equation. If it's compounding monthly, n will be 12. Make sure to put 12 as your exponent for n as well. So it'll be 30 times 12 as your exponent. When you type that in your calculator, if you type it in correctly, you get $741,349.13. All right, so that's one new formula dealing with compound interest. Now the next one we're going to do is one that I affectionately call PERT. And the reason why we call it PERT is you can see the formula right here. So it's principal times E, and then our exponent's rate times time. Well, what the heck is this E all about? Well, let's use this scenario. So this is how they came up with our value for E. So remember the amount that the formula that we were just talking about, where we would have, let's say if we had a $1 investment, so that's your principal amount, times 1 plus R, so 100% interest rate, so 1.00 is a decimal, and N in this case is what we have in our table, and then we'd have n times 1 as your exponent. So if you're to plug in n, replace n with 1 into this formula that I just put in here, you would get 2 as your answer. If you would replace, well, maybe instead of circling, I'll highlight. If you were to replace 10 into those two places where I highlighted, you type that in your calculator, you get 2.59. If you put 100 in your calculator, you get 2.7. And then you get 2.72. And if we continue to round to the nearest hundredths place, you'd continue to get 2.72. So this is an approximation. This value that we're finding here is what we call our value for E. So an approximation for this, again, it's approaching 2.72. That's where E comes from. Technically, E is a value kind of like pi, where it just keeps going infinitely forever. And it doesn't follow a particular pattern, so it's an irrational number. So we can round it to 2.72. Otherwise, your calculator will also have this button. I'll show you. So if you look at your calculator, the E button is right above this button here, which is ln. So look for your 4 on your calculator. To the left of that, you see your ln. That's something that we're going to learn about later. And then above it, you have e to the x power. If you have a scientific calculator, I can't show you on my screen right now, but if you have a scientific calculator, it's the same button. You look above the LN button. Above it is E to the X on most scientific calculators. So that's a button that we're going to be using for this next section. Everything else is the same. Your principal is still your principal. The rate is still the rate as a decimal. E is just your number on your calculator, and T is your time if you want to write those values in. But it's no different from what we had on the front page. So let's just jump right into this. Regina invests $12,600 in an account that earns 3.2% annual interest. Let's stop there. So I want to make sure that we change that to 0.032. Move the decimal to the left 2 places. Compounded continuously. Okay. Anytime we see that phrase, compounded continuously, that tells us that we're going to use that formula, E equals PERT. Principal times E times with an exponent of rate times time. Okay, so that's what that tells you, compound continuously. All right, what is the value of the account after 12 years? Round your answer to the nearest dollar. All right, so let's plug this in, or let's set this up. So it would first be our principal is 12,600. And then E, which again will be a button we use in our calculator. Our exponent is going to be our rate, 0.032, times our time, which is 12 years. I want to show you something. When you type this in on your calculator will automatically know as soon as you type in E that we're going to need an exponent. So if we're using a graphing calculator, let me get out of this graph. Just clear all that. So I'm going to do 12,600 first. Times E. So again, the E is above the L or EX or LN button. So to the left of 4, you want to type in second first, and then type the LN. Whoops. Hold on a second. Let me start all over. 12,600. I hit alpha instead of second. So times second. There we go. LN button. All right. So now notice, like I said, it gives us the exponent. If you're using a scientific calculator, it'll show this caret. And followed by parentheses, knowing that whatever we type after that will be an exponent. So we're going to include in that both the 30, or 0.032 rather, times 12. So this is our rate times our time, which was 12 years. So when I hit enter, we get approximately 18,000. If we round to the nearest dollar amount, we'll just say $18,499. All right, so let's see what it would be after same situation, or no, new situation. So it says Abdu invests $125,000 in an account that earns 4.7% annual interest, compounding continuously. So again, that tells us that we're going to use PERT here. What is the value after 15 years? So I want you guys to try this one on your own. So why don't you guys go ahead, set this one up. Don't forget to change 4.75% from a percent to a decimal. So go ahead and make sure you do that and use the same formula and hit play when you're ready to check your answer. All right, how did you do? You should have gotten 254,885 as your answer. If you didn't get that, here's how you set it up. So we start with your principal amount, 125,000, and then times E, and then our exponent is going to be 0.0475 times 15 years. So like I said, when you type that in your calculator, you end up getting $254,885. Oops. If you round that to the nearest dollar amount. We're going to skip these next examples, but down here below you see a summary of all the different types of exponential models we could use. They're all based on this original a times b to the x power, but these other ones use the same principles and would be the same graph. So good luck now as you work on the rest of your assignment.